Yeah, welcome here to this talk on frequency. It's a talk for a friend of mine, for Trey, and I thought I may as well just put it on YouTube as well. So all I did is I put some notes together, handwritten notes, put them on a PDF, and I'm just gonna go through the PDF. It's about how many pages? 5 pages. That's all it is. Okay, so the questions we are asking here tonight, or I'm asking, is what is frequency? What is wavelength? What is the difference between sound waves and electromagnetic waves? And I think I've covered it all. So we're going to look at into infrasound and ultrasound. We're going to be looking into the electromagnetic spectrum as well. So that's what we're going to cover in this little talk. I hope I get it done in a quick time. If you hear some banging behind me, it's New Year's Eve at the moment, so I don't know whether they come through the microphone. So people are letting their rockets off well before the time is due. Okay, let's go through the talk. So first of all, frequency is a function, and it's 1 divided by time, and time measured in second. Also, let me see whether I get the mouse to work. I get it to work. Just follow the mouse if you are watching on YouTube. Frequency, the definition by frequency is that there's a change occurring. So we've got a change here on this waveform. That's my 0 volt line here, or my zero line here right in the middle. And then it goes up, and then it goes down and back to 0. Yeah, and then it reverses on itself and it goes the opposite direction, goes down and goes back up again until it hits the 0 line again. And it repeats itself. So going all the way up and going all the way down and then back up again, that's considered to be one cycle. And what we measure is how many cycles or how many repetitions of this cycle have we got in 1 second. And that is the definition for frequency. Okay, we will be looking at a couple of, where does this happen in real life, and where are we bothered about frequency? I mean, there's a frequency. Again, if you take this term a little bit further, every year is a frequency. So every year repeats itself. Yeah? We've got frequency in a clock. Yeah, that you've got the. If you take an old mechanical clock, you've got like your spirit and the thing which goes to and fro once a second, supposedly, or several times a second, but it oscillates and it goes to and fro, and that's what we define as frequency. Okay, the human hearing is the big one, and if you look at a magazine, or you buy an amplifier or something like that, what you would find is they would look at the frequency range. So give you the power rating and all the great things about this amplifier, but they will also give you a frequency rating, and the standard frequency rating they give you is 20 hertz to 20 kilohertz. So kilo stands for 1,000. So it's 20 hertz to 20,000 hertz. So it's 20 of these cycles a second to 20,000 a second. Yeah? And that's supposed to be the frequency range. Now, generally it's said that's the range of human hearing. I doubt that there are many humans that can actually hear within this range. What is more realistic is around about 35 hertz, and then it goes up to 15 kilohertz. If you get older, your hearing tends to drop off at about 8 kilohertz, maybe even lower than that. So higher frequencies you won't hear anymore. Young people will be able to hit about 15 kilohertz, possibly even go higher than that, possibly go to about 20 kilohertz, maybe. Yeah. The range decreases with age. Yeah. There's also some interesting stuff. There's some device which was on the market some time ago, and very often young people, they tend to loiter in shopping centers. Yeah, so they loiter around shops. So they got a device and they called it the mosquito, because mosquitoes have got this high pitched sound when they make their noise, and that sound is supposed to be 15 kilohertz. And it's a very uncomfortable sound. So the whole idea is that they put up a mosquito around the shop, and young people will scatter. They will not stay anywhere near the shop, and older people just won't hear it, and they're not bothered by it. So that mosquito was around. There was a big question, is it legal or not? Can you do this? Is it discriminatory? And things like that. And I think here in the UK they decided that it was legal at the time. I'm not sure what the situation is now, but anyway, there was a problem like that. I think I haven't heard a lot about it recently. I don't think loitering is as much of a problem as what it used to be, but just to give you an idea, the whole thing about human range. Now, what frequency are we talking about? We have got air, which is compressed and decompressed in this cycle. So we generate an electrical pulse. That pulse drives a coil. The coil then is connected to is put together with a magnet, permanent magnet, and is connected to a membrane. And as this signal goes through the coil, the membrane just vibrates to and fro, and you get air moving, compressing and decompressing. I think the proper term is compressing and rarefying. So that is basically what's happening with sound, yeah, and the way sound is generated. I hope it makes sense to you. Okay. Right, let's have a look at some of the other stuff which is about sound. Sound below the hearing range, so that's called infrasound, and it's typically less than 35 hertz. And I tried it out with students, so I used a signal generator. I put a loudspeaker with a tweeter, connected it to the signal generator, and I was looking at the lowest range students were able to hear. And it was about 35 hertz, round about there. For most of them, the hearing kicked in. For some a bit earlier, for some a bit later. And one sound you're quite familiar, you're possibly familiar to, is the 50 hertz or 60 hertz humming sound from a transformer. And that humming sound would be from power supply or something. Or when you go near a power station and you've got these big transformers, so you would get this humming sound. Okay, now we are looking at sounds you cannot hear, but they can still affect your body and they can still affect your well-being. So, for example, we've got wind turbines, and when they turn round, they are supposed to generate very low sounds, very low frequency sounds. Sort of a rumbling noise, which is very often below 35 hertz. So you can't really hear it, but the waves are quite powerful, and you can feel it. And some people seem to respond to it. And there were complaints that people were saying that who had a wind turbine installed near their house, that they couldn't sleep anymore, and they were waking up. They felt that they had anxiety and headaches and things like that. And that's actually real. And people know that this is the case, and in the military this effect is being used, but the wind turbine operators, they were just putting up the turbines, and those things were spinning around at a very low level, and they would produce those frequencies, and they just didn't care, or it didn't come into their thinking or whatever. And it probably doesn't really matter if it's set up in the middle of nowhere and people are not anywhere near it, but if it's near a residential area, then these sounds will travel, and they will, especially low frequency sounds, will permeate brick. They will go through solid structures, and they can actually travel quite a long distance as well. There's also something called the brown note. Some people say it is not real, but I had and I'm going to talk about it a little bit more in a bit. It's basically just where your body responds to low frequencies and does stuff you don't want it to do. There are geological phenomena as well, and they are very low frequency signals, possibly less than a hertz, so one change in 2 or 3 seconds or whatever, and animals seem to pick up on it. So when an earthquake comes, very often you find that animals know that something is taking place, and they get scared, and they're looking for higher ground or for something else. And so animals have been sort of a predictor for geological phenomena, and some people who live in earthquake zones, they know if the dog gets restless or something is going on, something is happening. So we've got rumblings as well, so they are sort of barely perceived, and they can be quite annoying. An interesting thing as well is a lion's roar, which can be heard up to 5 miles away, and it is meant to have, and I was looking it up, it was meant to have about 114 decibels, and it goes from 33 or 250 to 250 hertz. So that's a really low frequency, and again, it can travel for long distances. So the noise level is about 114 dB. So we're going to hear this decibel to measure the level of noise. We're going to hear this figure quite often. So let's have a look through that. So 10 decibels is breathing, and normally the problem is that our ear is not linear, but it's logarithmic. So when you double the amount of noise, you just think it's a little bit louder. Yeah, and so they came up with a decibel scale to make it more real. So about 3 decibels is roughly a doubling of the sound. But the difference between breathing and an air raid siren is about 1 million. I hope I got this right, but it's very high. It's about 1 million. I think, if I got my math right, possibly even more. But there's a massive difference between it, yeah. So it's not just twice or 3 or 4 or 10 times as noisy, but it's many, many times noisy. So the decibel system was introduced to make it a little bit more real. So breathing in a quiet office might be there might be, you know, even though on the electronic scale, if you were to measure the sound, there's a huge difference. But in your perception, it may not be that much of a difference. Okay, so just to give you an idea what those decibels stand for, 10 decibels is breathing, 50 decibels a quiet office, 60 decibels speech, 70 decibels a noisy restaurant, 90 decibels a tractor. I think in the EU, when you've got garden equipment, like a lawnmower or a strimmer or something, they have to be reduced to 96 decibels. And so that's somewhere between tractor and factory noise. Just to give you an idea, so these systems are well in place. So at 110 decibels, it's uncomfortable, and that's pretty much where we find our lion's roar at 114 decibels. And then at 120 decibels is a disco or shotgun, just to give you the idea. So that's very, very loud. I know what a shotgun sounds like, and you're advised to have hearing protection. And 130 decibels is an air raid siren, yeah, and it doesn't take a long time. It becomes very, very painful to the ear. A lion's roar, 114 decibels. Okay, let's go back to the brown note. So the brown note is infrasound, and is sound below the hearing range. So that's below 20 hertz or 35 hertz, whichever you consider to be the hearing range. It is supposed to be between 5 and 9 hertz. I some time ago for the brown note, I heard that it was 18 hertz. Whatever it is, I don't know, but it's somewhere low down. The whole idea is that it cannot be heard, but it can be felt. And if you ever if you've got access to a signal generator and a loudspeaker, I would recommend that you just hook it up, and the levels of a signal generator are pretty low, so you don't need to worry that you lose control of your bowels or anything like that. But you can actually, when you put your hand in front of the loudspeaker, you can feel the wind just going, hitting your hand and going to and fro. And that's rarefying and compressing the air when you feel it. And anyway, if you increase the level, the decibel level, to about 120 decibels or something, so you've got like a lot of air going to and fro, and it does something to your body. Yeah. So some people say there's a need to relieve oneself, so the colon empties. And my former boss, he used to be a rock musician, and he was telling me that they were doing this as a bit of fun at the end of a gig, that they put the brown note on, and people were dancing, and suddenly they were rushing to the toilet. There are some stories on big rock concerts where they've done the same thing, and something happened and people needed to very go to the toilet. I don't know whether I've got it on these notes. 12 hertz is some sort of resonant node to the human body. So it does something to your body, and this is where your ligaments are attached and so on. So if you've got like a sound wave of 12 hertz, it'll have quite an impact on your body. So it might even be the brown note. Yeah. So all I'm saying is there are low frequencies, and they're doing something to you. One of the things is anxiety. There's a need to relieve oneself. Military have been using this technology since, from what I was reading up, since the Second World War, where they were producing frequencies like that to try and scare people. I've spoken to a gentleman who was in the Israeli army, and he was telling me in the Intifada they used different things, that they had speakers for crowd control, and so they were pumping out certain frequencies to try and get people to move away, to go away. And it could be the the low frequency stuff, the infrasound stuff. Could also be the ultrasound stuff, or the 15 kilohertz mosquito one, that it's very uncomfortable and people just want to go away. Okay, let's take it a bit further. Apparently elephants communicate with infrasound, so they've got like 14 to 20 hertz signals, and this goes from 85 to 95 decibels, so it's fairly loud, just to go up the list. So that's about noisy restaurant and tractor, so you can't hear it, but they use it, and they've got, like, from what I was reading up, it's like 10 second, 14 second intervals. And when these sounds are replayed to elephants, they sometimes do certain things, that they stand still, move forward, move towards the direction of where the sound comes from, and so on. So it does something to them, and they can perceive it as well. Another thing as well is the lower the frequency, the further the range. One example is when when somebody's playing his bass in the car, and the high notes as well, you can hear the bass from a long distance away, but you don't hear the high frequencies. Yeah. Also, lower frequencies are traveling better through solids than higher frequencies. The next one is sound travels faster and further through denser media. I've got this note here, 12 hertz is a resonance for the human body. So again, there's something to it, there's something to look into. Okay, and the last one is this wavelength. Yeah? So this wave which we have got up here, that has got a length. Yeah? And what you find is you can actually measure it. If you could color the air where the sound is traveling through, you would see that it would compress and rarefy at a certain wavelength. I've got did some calculations, and I can go through this in a minute. Anyway, wavelength is defined by, it's called lambda, so that's this Greek letter L for lambda, and then we've got V for velocity and F for frequency. So velocity is the speed of the sound traveling through the media, and when we've got air, the denser it is, the faster it travels. And it's interesting as well, and I'm not sure how it would impact it and how big the difference is, but if the air becomes thinner, the speed is going to go down. So if you're on top of a mountain and you're talking to somebody, the speed is going to be less than being, at the bottom of, not at the bottom, but at the Dead Sea, where you're below sea level, and the air is really, really thick. So that makes a difference as well with the speed. Okay. So we've got this. Let's move on with ultrasound. So ultrasound is anything over 20 kilohertz. And I've seen some interesting definitions. So 20 kilohertz is something you and I cannot hear, most likely. A baby might be able to hear it. Your dog will be able to hear it. Your cat will be able to hear it. But we won't. Yeah? And ultrasound can go up to 18 megahertz. And there were even some suggestions that it goes up to 3 gigahertz and so on. So 18 megahertz is very, very high. So M stands for million. So that's 18 million cycles a second. Yeah. So again, when I look at this waveform here, so 18 million of these things in the air, of molecules rarefying and compressing and rarefying, or compressing and decompressing, 18 million times a second, and that's what goes into ultrasound. I'm not sure how it's used, whether it's used at all, yeah, but it can go very high. I'm sort of aware of ultrasound systems which go up to a couple of hundred kilohertz, so that's a couple of 100,000 times rarefying and contracting the air molecules. Okay, just a little bit of dogs can hear up to 45 kilohertz. Bats, they can sort of hear between 100 and 200 kilohertz. I think this figure, I need to revise it. I've read some stuff that the mating call of bats is somewhere at 76 kilohertz and lower down. You can buy bat detectors, and it's basically just a frequency divider. So it takes a signal from a bat, divides the frequency by a factor of 10 or whatever, and it brings it down to the human range. So you can have your bat detector where there are a lot of bats flying around, and you can listen to some sort of representation of what their calls sound like at a lower frequency you can actually hear. Cats can hear up to 64 kilohertz, so again, they can hear into a spectrum you can't hear at all. Yeah, it's quite interesting. So there's a whole world out there of sounds which we are denied. We cannot hear it. Cats can hear it, dogs can hear it, bats can hear it, insects can hear it. I try to figure out some of the insects, how high they can hear, but I didn't find any information on that. In general, animals can hear about 10 times higher than us, or up to 10 times higher, which is up to 200 kilohertz. So again, a whole world of sound, which we are denied. So one of them is infrasound. That's a sound below 20 hertz or 35 hertz. And then it's the ultrasound as well, where it goes the other direction, the other extreme. Talking about the sound and about the human range of hearing, let me just go back here. I've heard some stuff that students, when they got their smartphones and they had text messages, they would put a tone out, a calling tone or ringtone at 15, 16, 17 kilohertz. And that was just to fool the teacher, so they could hear it, but the teacher couldn't. Most likely, providing the teacher was a lot older than them. And that was sort of a joke going around, so they could send text messages to one another, and they would hear what's going on, but the teacher wouldn't. And that's with your hearing tending to drop as you get older. To be fair, the old telephone system, when you listen to that, the frequency range is only about 2 kilohertz, 2.3 kilohertz. So it goes from about, I think it's from 300 hertz to 3 kilohertz, around about there, 3.4 kilohertz. So it's about 3 kilohertz. It's very, very limited. And then right in the middle of the old analog telephone system, they had some bands which were cut out, and they were just used for signal transmission. So they, for billing and stuff like that, they were putting some signal through. Okay, let's move on with this. Done this ultrasound, very interesting. Okay, what does ultrasound do? So we use it for materials testing. Apparently there are systems about which go from 2 to 10 megahertz. So they've got a very high frequency. Again, air is just moved, air molecules are moved, that's all. And it penetrates the material, and to get some reflection, then based on that, they can test the material. Imaging is done at about 2 megahertz. Plastic welding is done between 15 kilohertz and 40 kilohertz. Never had anything to do with plastic welding, but apparently there's a method where you can join plastics together by vibrating the air molecules 15,000 to 40,000 times a second. Cleaning is done between 20 and 100 kilohertz range. So if you get your embroidery, like your golden rings and diamonds and whatever, and you go to a jeweler and you ask him to clean it, they put it into a little box. The box generates ultrasound, and it can go up to 100 kilohertz. Yeah? And that makes all the dirt vibrate so that it just falls off. Destructive medical ultrasound is at about 1 megahertz. I'm not sure whether they use it for killing or destroying kidney stones or anything that is hard, where it doesn't affect soft tissue as much as hard tissue, but it then destroys the kidney stones and they disintegrate. Again, I don't know how it's done. I know ultrasound is normally generated using something which is called a piezo crystal. They're small crystals, and the frequencies applied to them, and they start vibrating at very high rates. Okay, back to wavelength. The speed of sound is about 340 meters per second. So 20 hertz, the wavelength is about 17 meter. At 20 kilohertz, it's 17 centimeters. So if you could see the sound in the air, or you could make it visible somehow by coloring the air molecules, at 20 kilohertz you would see something like 17 centimeters. At 20 hertz, the sound wave would be, as long as, I don't know, is it a football field? How wide is a football field? It's probably not as long, but as wide as a football field, but I'm not sure. Okay, in water, denser medium, yeah. So the speed of sound is 1,500 meters per second. So it's a lot faster than in air. So you can see it's got something to do with the density. And for air, you've got a definition that is at ground level and at 20 centigrade, yeah, so that the air's got a certain density. And then you come up with this figure of 343 meters per second. In water, it's 1,500 meters per second. And then at 20 hertz, it would be 75 meters. At 20 kilohertz, 75 centimeters. And you can see it's all a little bit longer, or longer than in the air, the wavelength. And that's maybe the reason why sound in water tends to travel further than what it does outside the water. And then when you go further down and you go to lower frequencies like 1 hertz or a couple of hertz, like ship propellers and stuff like that, you can hear them over a very, very long distance. Okay, we need to look at electromagnetism as well. So the speed for electromagnetic waves, so that is when, let me just take you to a diagram. When you put a current through a wire and the current goes to and fro, goes this direction, then it goes the other direction, this direction, so it just toggles all the way. So whenever current goes through a piece of wire, it generates a magnetic field, and the magnetic field orbits the wire. And so this magnetic field goes one way, the other way, one way, the other way, depending on how the current flows. And this magnetic field then in turn generates electromagnetic waves, and electromagnetic waves can be picked up using a radio or a receiver. Yeah? And so that's where we've got wireless communication from. Again, when I look at the speed, the nominal speed, which is always assumed, is just a nominal figure, which is 300 million meters per second. I didn't scan it right. All right, so this is meters per second. But the figures are not quite right. So in air, it's 299705000. In a vacuum, it's a bit faster. It's 299792458 meters per second. And in water, it's very slow. Yeah. So we've got this figure here. So it's a little bit different to sound waves. Because a dense medium will actually slow down the wavelength, the electromagnetism. It's the opposite way around. Yeah? So if you just generate sound waves inside a solid, like you knock on a door or you knock on a mountain or something, on rock, you can hear it for a long distance and it's very fast. Yeah? If the medium gets thinner, it's very, very slow. But with electromagnetism, it can travel through space really, really fast. And as the medium gets more dense, the speed goes down. The speed still is so fast that for all intents and purposes, you won't notice it. It's just electronically you can pick up the differences, based on phase shifts and so on. But you don't really notice a difference in speed. Okay, wavelength. We've got a couple of wavelengths here, and we've got 1 megahertz, so that's in the AM radio band. And so if you've got like a full-size antenna to accommodate the full wave, it needs to be about 300 meters long. There are some methods we do to shorten the antenna length, because if you put a 300-meter tower, which you use as an antenna, it would be very expensive. So there are ways and means to shorten it. One of them is using coils. The other one is in order to get the radio wave to emanate or to propagate from the antenna, you only need about a quarter wave. So that would be 75 meters. And that's a bit more manageable at 1 megahertz. At 100 megahertz, so again, that's a broadcast band. That's about, where you've got your FM radio. That's 3 meters, the wavelength. So a good antenna is about 75 centimeters. And when you look at the olden days, every car, this was pretty much the length of the antenna was about 75 centimeters long to operate. Then 1 gigahertz, that's where your mobile phones work. That's 1 and 2 gigahertz. So that's 30 to 15 centimeters. Then we have got 2 gigahertz, that's 15 centimeters. So that's again Wi-Fi. Your microwave oven is 2.4 gigahertz. And then 10 gigahertz, that's where you have satellite television. The wavelength is about 3 centimeters. Again, the antenna would only be 1.5 centimeters in length to deal with that. And we use dishes and stuff like that to amplify the signal. Okay, we have got infrared. Infrared goes from 300 gigahertz to about 400, and it's cut off on the scanner, 400 terahertz. UV light goes from 100 to 400 nanometers. And it's over and above 750 terahertz. Yeah. And then we've got UVA and UVB. And we've got the wavelength here. So 380 nanometers, 350 nanometers, 280 to 100 nanometers. Apparently UVB is what we need for our body to produce vitamin D, and the sun produces it. It's not harmful. I'm not sure whether it's UVA or UVC. One of them is quite harmful. So that's the one that gives you sunburn and can cause skin cancer and lots of stuff. But UVB is something we need desperately for our bodies so that our body will produce vitamin D. And if you live in the northern hemisphere and you're as far up as we are, I think we only get it from May to July over lunchtime, UVB. The rest of the year we don't get it, so we have to tank up in that time, or we have to get like food additives to try and make do. But you can see that that all this stuff is all kind of interlinked. So we are looking at light as well. So between infrared light and UV light, we've got normal light. And we're going to look at this in a minute in a bit more detail. Okay, let's move on. We've got the electromagnetic spectrum. I've got like a little list here, and you can see, you know, what is there. So we've got 50 hertz, so that's the main sum. And that's the way power is transmitted. Yeah, so you can pick it up if you're near a high voltage pylon. In America, it's going to be 60 hertz. Here, it's going to be 50 hertz in Europe. And pretty much the rest of the world, I would say, other than the Americas. And those high voltage pylons, they've got huge amount of current, very high voltages, transmit vast amounts of power. So we're looking at potentially megawatts that are transmitted through those lines. And you get like really strong magnetic fields. There are some studies which suggest that the rate of leukemia is higher for people who live underneath high voltage power lines, significantly higher. So that is, again, there's some research done, and I'm not going to go into any detail here, but it's something to look into and to make sure. One personal experience was, I'm into, this is my world, electronics, frequency, anything to do with this. And so I surround myself with these things, and I remember that in my bedroom there were like loads and loads of equipments, you know, which I was dealing with and playing with and so on, and I never slept very well. And I once sort of took just an electric field tester, so it wasn't a Tesla meter as such, just for electric fields. And because I had wires sort of trailing around my bed, and it sort of went in a 90-degree angle, so where my head was, there was a fairly high levels of electric fields. Yeah. So I thought, maybe that's the reason why I'm not sleeping very well. So all I did is I turned my bed round, and I put my feet where my head was, and my head where my feet was, and I slept really well. And I was out of this. My head was out of these electric fields. So for me, it wasn't just psychosomatic, but there certainly was something to it that is not good to sleep surrounded by electric fields, yeah, or electromagnetic fields. So it's a good idea to switch your electrics off, even disconnect them, and maybe have good earthing as well, so that you put it around your cables, and might be better for you. Okay, 20 kilohertz is audio to a speaker, so that's what you find as well, sort of in your systems. 20 kilohertz. Also, if you have a current at 50 hertz, it can be quite lethal. As the frequency goes up and you get a shock, let's say 100 kilohertz or something, it is less lethal and it tends to not kill you as easy as 50 hertz, even though the current may be at the same level. So 100 kilohertz, so again, that's the stuff that goes through the wire. So I'm not talking about air now. So this is the electricity or the electricity, the AC going to the speaker, not the air being rarefied. Now at 100 kilohertz, we've got long wave, and these waves they tend to follow the curvature of the Earth, and you can hear long wave signals maybe about 1,000 kilometers away without much of a problem. So they follow the curvature of the Earth, and you can transmit beyond the horizon, but the band available is very, very little. As you go further down, you go to 30, 40, 50, 60 kilohertz. In between those two allocations, the waves can even penetrate water. So submariners, they use these low frequencies and to communicate and to transmit to the surface station, to their base, which is over the water. And again, they use slow Morse, and it's very difficult to communicate because you haven't got the bandwidth really at these frequencies, but there is a possibility to do this. Okay, so that's 100 kilohertz. Then we've got 1 megahertz. 1 megahertz is smack bang in the middle of the AM band, also called medium wave. And in Europe, it's pretty much discontinued. In America, it's pretty much alive. And you've got it goes from about 540 kilohertz to 1.6 point something megahertz. And again, at daytime, it follows a little bit the curvature of the Earth, so you get over the horizon communication. But in at nighttime, it goes even further, and it's to do with the ionosphere. So it bounces off something which is called the E layer at nighttime, and you can listen to it, throughout a whole continent. So, for example, here in Europe, in England, you used to be able to listen to radio stations coming from Russia and the Ukraine. In America, you could listen to one side of the country to the other side of the country. Okay, then we've got 3 to 30 megahertz, which is considered to be the shortwave band, and there's broadcasting in there, and still there, you can still find it, and there's also long distance communication. Before the advent of the internet, this band was guarded like crazy. That was so important for long distance communication. I've noticed, and it was quite interesting, when I went to London, I saw a lot of embassies, and they had massive directional shortwave antennas on their roof to communicate with the mothership, so to say, with the host country, the mother country, not the host country, the mother country, and to get messages to and fro, not relying on the telephone system. And that was quite interesting to see that they had all these things sort of set up, and the type of antennas they were using. Okay, shortwave broadcasting is normally on the ground wave. It follows a little bit over the horizon propagation, but not much. But then the main mode of propagation is it hits the ionosphere, and there are 4 layers. There's the E, the F1, F2, and there's also the D layer. Now on shortwave, you are working with the E layer, the F1 and F2 layer, and the signal bounces off. It's like a massive mirror in the sky, bounces off and then comes down again, and you can easily cover distances going in excess of 1,000 kilometers and more. So that's not a great achievement to do more than 1,000 kilometers. It's a little bit sort of hit and miss. broadcast stations, they use huge power levels, and I used to regularly listen to, here in Europe, to an American Christian broadcaster, and it was fairly reliable. So when I turned it on at a certain time of the day, I could hear them. But again, propagation conditions change between day and night and between summer and winter. So you've got a range of frequencies, and you need to find out which is the best frequency for the target audience. Okay, we're going to go on. We've got VHF. One thing I want to say about medium wave and about the health implication. There used to be an AM transmitter, I think it was Langenberg, somewhere near the Luxembourg border, or the Saarland or something. I'm not sure. I think it was called Langenberg. And they had a very powerful AM transmitter on this hill. And people weren't far away, weren't living far away from the transmitter, but there were some people who were quite nearby, and they they found out, and it might have nothing to do with that. Yeah, sort of correlation doesn't mean it's causality. Yeah, this is very important. So if there's A and B, and both, you've got high power and you've got longevity of the people, doesn't mean that there's a causality between the two of those, but it could be. Anyway, they noticed that these people who lived in the proximity of the transmission tower of the AM radio station, they all lived into the hundreds. Yeah, so nobody died young. Most of the people they died in their 90s and went over 100 and so on, and it was quite noticeable. It was sort of a statistical blip for this area. Has it to do with the transmitter, the medium wave transmitter, the AM transmitter, or not? Don't know. Medium wave transmissions in Europe have stopped now from most places, so there's not very much going on there now. So will be interesting maybe to, a university to look at the data and see whether it's not just an accidental correlation, but there's actually some causality there as well, that this is the reason that people live longer, because they live near a 1 megahertz transmitter at high power levels. Maybe killing of cancer cells, I don't know. Okay, next we've got 30 to 300 megahertz. That's the so-called VHF band. It's the FM broadcast band, so that's from 87 to 108 band. Then we've got the air band, so for air traffic control and aeroplanes talking to one another. That's between 108 and I think 136. Then we've got the marine band, which is about 170. Then we've got industrial band as well, where, for industrial radio systems, and they're run about 150, 160, round about there. Then we've got UHF, which goes from 300 megahertz to 3 gigahertz. And that's typically a TV broadcast. So the wavelengths here is from 10 meters to about 300 megahertz. What is it? That's about... I'm just trying to think. 144 is 2 meters, 1.5 meters, isn't it? 1 meter? 1 meter. 1 meter. 1 meter in wavelength. 10 to 1 meter in wavelengths. And then we've got 300 megahertz, so that's 1 meter to 10 centimeters. That's right, isn't it? Yeah, that's right. So the antenna would only have to be for 10 centimeters, 2.5 centimeters in size to allow it to, bump off the little radio waves. We've got TV, we've got cellular, GPS is in there as well. That's at about 1.3, 1.4 gigahertz. We've got radar as well. Radar goes from 400 megahertz all the way up to a couple of gigahertz. And so that's all in this band here. So it's quite lots of frequencies, lots of channels in this section, in this band, but it's there. Okay, 3 gigahertz to 30 gigahertz. So we've got satellite TV, so that tends to be about 10 to 14 gigahertz. At about 10 to 14 gigahertz, rain becomes a problem. So when you've got a satellite dish and you try to you try to watch your favorite TV program and you've got a very rainy day, the higher the frequency, as you head towards the 14 gigahertz, you get like a massive deterioration of the signal. So that's one thing there. There's also, it's called the microwave band. So again, the frequency here at 3 gigahertz, we're looking at 10 centimeters and it goes all the way down to 1 centimeter at 30 gigahertz. Wi-Fi is at 2.4 gigahertz and at 5 gigahertz. So we've got those two bands there where we find the Wi-Fi section for computer. And the reason why they use 2.4 gigahertz is that they use the same frequency for the domestic microwave. And they couldn't use it pretty much for anything else. They couldn't use it for satellite communication because the communication would go down at lunchtime when everybody turns on their microwave. Okay. Beyond, we've got infrared light, we've got UV light, X-rays, and we've got normal light as well. And the big question is, what are the implications when we look at you know, all those frequencies and everything which is there? We talked a little bit about the psychosomatic stuff of waves which are sound waves. There's some stuff as well where they put electrical signals into the brain at certain frequencies. It's something to go into and maybe to explore a little bit further. So, for example, I'm not sure what frequencies they're using. I heard it ages ago, but they put some electrodes on the head, and they put some low-level signals through there, and people feel that there's someone behind them, yeah. Or they feel anxiety, so they panic, or they feel like they are in heaven. Yeah, something like that. So they get like weird sensations by putting signals onto their head. Yeah, with small electrodes, small signals, so they don't get an electric shock or anything, but they're just certain frequencies they put in there. As far as I understand, they're fairly low frequencies they use there, but they are not sound frequencies, but they're electric frequencies. Yeah, so they're electromagnetic frequencies. So they're very low. I think it's in the 20-30 hertz section. Medical implications, 50 to 60 hertz. If you live under a high voltage pylon, there's a higher chance of leukemia. That's a study which came out in Sweden some time ago. Please check it out and you know, have a look through that. 1 gigahertz and above, again, there were studies and lots of anecdotal stuff which can cause tumors. So when people when the first phones came out, they were always at the highest power setting. They've changed everything since. But so people had about a watt or 2 watts, you know, of RF energy, radio frequency energy, at 1 gigahertz to 2 gigahertz right next to their ear. The wavelength is between 30 centimeters and 15 centimeters. At 30 centimeters, you've got one current eye on the other side of your brain. So the tissue is going to heat up. And it could potentially cause damage to your brain. If you use a 2 gigahertz, like 1.8 is a band, 2.1 is a band, I think it's 1.9 as well. So if you use frequencies around about 2 gigahertz, the wavelength is about 15 centimeters, and you get 2 current eyes in your head, one on the far side, one on the near side, to where the phone is. And again, it can cause a lot of damage. Human tissue tends to suffer once you go over 40 centigrade. So that's a problem. So we've got high levels, especially at high levels, it's a big problem. At the low levels, we don't have these effects so pronounced, so it should be okay. And some people claim effects of RF. So they feel if there are sources of RF around, it makes them anxious. It gives them a hard time. They don't feel relaxed. They don't feel easy, and it's a problem. So they put themselves into a Faraday cage, and which is just like a chicken, you know, a box made of chicken wire. They put themselves in there, and they sleep inside there, and they feel it's a lot more relaxing, and there's no RF getting anywhere near it, and they feel okay, and they earth the whole thing, and everything is fine. Another thing as well, and this is about sound frequencies, and I didn't mention it here, but I'm just gonna make a point of this. When you look at guitars and musical instruments, they're tuned to a note which is 440 hertz, which, if I'm not sure whether I get this right, but I think it's A, or the note A. I'm not a musician, so I'm not sure. Apparently the natural frequency is 432 hertz. And so if you tune your instruments based on the fundamental of 432 hertz and then a multiple of that, and you play your music, it's a lot more healthy, wholesome, pleasant to listen to than having instruments tuned to 440 hertz. Some high-end musicians, they've latched onto this and they've retuned all their instruments, and they use 432 hertz plus the harmonics, so which is like a multiple of 432. And then others have used, are still using the 440 hertz, yeah, which is apparently some EU standard or something. And it's been decided that everything has to be tuned to that frequency. Maybe it was just an easier number. It's something to look into. I did some experiments where I used Audacity and I slowed a song down, made it sort of tune into 432 hertz. It didn't sound much difference, but I was testing it with a couple of people, asking them which of the two identical songs, which of them makes them feel more relaxed. And most of them came back, and it might just be coincidence, it might be real, it might just be junk science what I'm doing, but most of them came the one that was tuned to the natural frequency of 432 hertz. So again, guys, something to check it out and to look into. And that's all about frequency. What did we look at? We looked at frequency, the brown note, the ultrasound, looked a bit of that, and wavelengths, what wavelengths is all about, and a little bit of the electromagnetic spectrum, how this all works together. Hope this helps. Thank you for listening, and if you're interested, maybe more on this later on.